Good morning, everybody. Are you there? Good morning, everybody. Are you there? Hello. Good morning, everyone. Hello, hello. Captain speaking. Crew member. Are you there?
Good morning.
Good morning, William. Is it just you and me now?
Lila's here too, but I don't know if she's talking.
Okay, let me see. Oh, Parissa? Okay. When I checked the Dropbox, I found only 6 students had submitted the report. I think they're still busy with the Dropbox, maybe. Hello, hello. Are you able to see my screen?
Yes, the Zoom. Yeah, your beach board now.
Yes, good, good. Just want to put you on test. All right. No, I mean, put the system on test, basically. Okay, let me open up the file. Well, not everybody's here, so. I can't really get started yet. So William and Pereza, are you able to check the video? The video I uploaded, this is a YouTube video.
Yeah, I saw those.
And were you able to practice a little bit or try to do whatever the instructor was showing?
Yeah, it was helpful in the one where he had the 3D model and he showed on the model where the hydrogens would come from.
Exactly, exactly. This is something I don't think my Zoom lecture will be able to show because basically this instructor was able to use a modeling kit and then with a whiteboard drawing at the same time. Right? And I don't think I can do that at home. I can do that at school, but not here. Okay, that's the problem. So we have 4 students now on board. All right, 6 more to go. So is everybody having a great time submitting the report, the Aldo report? Were you able to do the report without major hiccups?
Yes.
Yes. I heard Dr. Dr. Lopez gave a lecture on NMR yesterday. This is about coupling, but students were saying this information he released yesterday was actually pertinent to your report writing that was due before his lecture. So they were saying I need to give a special consideration for some of the information Dr. Lopez actually released after the deadline of the report. I don't go to his lecture, so I don't know what's going on. But my understanding is Dr. Lopez actually gave a lecture on Aldo experiments. So the calculus, and then the coupling constant calculation were all being covered. But
Yes,
that,
I remember him going over the Aldo experiment before classes were canceled.
okay, so that was
so
before spring break.
yes.
So he did cover. Was it a thorough lecture, or was just a like a introduction type of lecture? You don't know.
More of an, oh, I'm sorry, can you say the first part again?
Yeah.
I couldn't hear it.
I don't know whether his lecture before spring break was actually covering the material that you need for the Aldo report.
I used the lecture that he gave before spring break as reference.
Okay, great. So the lecture yesterday was something else then. His lecture on NMR.
I personally did not use what he said yesterday as reference for the report, but I may be wrong. I am not sure either.
Okay, so what was the topic yesterday for his NMR chapter yesterday? His lecture I'm talking about.
Benzene coupling constants, vinyl coupling.
On vinyl groups also? Okay, so basically cis and trans plus the Gemino on the SP2 then. Okay.
Yes.
Okay, so this is actually a review of the 320L then. Am I right? I don't go to his lecture, so I really need your inputs. Because when I lecture, I didn't really have a lot of time. Remember when you guys will have to get result or lab work going, I cannot find much time lecture to review the 320L, but I try to cover the calculus. Hey, wait a minute. I didn't do that with you guys. I did it with the Monday, Wednesday class. Okay, so, okay, now do you see the problem now? Because I have two classes, two sections, one scheduled before his lecture, one scheduled after his lecture. So I actually have I have to split my teaching. And if you guys need clarification from me, you should let me know, because I really don't know what he feeds you in the class. Understand? Yeah, okay. All right, so how many students we have now so far? I don't know what's going on. People don't want to show up on time for Zoom lecture for some reason. You guys were better on campus, showing up on schedule, but I don't know what's going on here. Anyway, I think I'll give another 2 minutes and I want to get going. I graded your pre-lab of the peptide reaction 2 during the weekend, and I spot several mistakes, and I actually made a file just to summarize the common mistakes, okay? And I think it is a matter of, do you remember to write it down? I'm pretty sure you all have the knowledge, but the thing is, do you remember to write it down? That's the problem. Okay. Mistake number 1, common mistake. Although I would say maybe students out of 12 are able to address the important issues which I cover in the class. This is about the diaster isomers. In other words, the starting material is stereospecific. You were assigned to do D or L. And so your product from reaction 1, from the protection group, okay, that one is a stereospecific product from reaction 1. And the starting point of reaction 2 is also stereospecific. But because of a TBTU and because we use base in this activation process to make the reaction go, the intermediate actually went through the change of sp3 hybridization to sp2, and then with the hydrogen deprotonated and then return back to the molecule. The starting material of reaction 2 already lost the stereo direction, the stereo specificity. And so I want you guys to give me, a specific starting point for reaction 2, but you need to give me a resonant mixture. At least you have to indicate, okay, the chiral center is actually not being able to conserve from the reaction 2. So a lot of people made that mistake, okay? Because I emphasize that, and actually that is the purpose of reaction 2. You want to study, okay, whether the TBTU works or not. And this is one big property you want to examine. So I thought this is important. So if you don't do that, you lose half point. Okay, the other thing is the molecules, okay, introduce triethylamine, and this is actually being used twice in the amount of moles compared to product 1 and also the amino group donor. And I actually lecture specifically about the 4M moles. If you look at the procedure one more time, okay, the 4 millimoles is being used because I lecture about it, so I want you guys to write it down. Because a lot of times when you do the workup, you're trying to get rid of the extra amount of reactant you added in, okay? I just want to show you right here. Okay, there is 4 millimoles of triethylamine added to the mixture. Okay, and look at your starting material, okay, the N protected amino group. From the reaction 1, you make that product 1. Okay, so this is your product 1, okay? And you're using only 2 millimoles. However, why do you want 4 millimoles of the amine to kick off the reaction? You have to watch out because you're using this L-aniline methyl ester hydrochloride. So I just want to show you one more time, okay? Okay, so half of the amount of the triethylamine will be used to deprotonate this hydrogen. The other half will be used to deprotonate this HCl, okay? Without that amine attacking this molecule, then you don't have a free amino group for the reaction of peptide, right? Okay, so this is the part I emphasize. I want you to tell me, hey, what is the purpose of 4M M moles right here, 4 millimoles here? I asked for it, so I look for the mechanism to show me that. Okay, so if you don't show me this part of a attack, then you lose half points, okay? So I can tell you the common mistakes, okay? One come from this chiral center not being conserved. The other mistake is actually this part not being pointed out, okay? You need that double amount of amine or the base to help proceed the reaction, okay? So another common mistake, I can tell you the highest score from this pre-lab was 9 points from my class, okay? So one student just made this 2 mistakes, and the rest, she was able to do perfect answer. So I can tell you this 9 points for this pre-lab is already record high. Okay, and I gave a big praise to the students yesterday. And so this is not an easy one, quite difficult. Okay, now the other common mistake, let me point out right here. DMF, dimethylfuramide, is miscible with water. Okay, if you look at the structure, now with nitrogen there and also a carbonyl group, okay, carbonyl group is polar, okay, and nitrogen, that means potential hydrogen bonding networking point, and it has polarity and it's high polarity, and this is miscible with water. And it serves to dissolve all reactants and products. Oh, we all know that, okay? But all the ions and the fragments from uranium salt, and then the chloride, okay, you remember, okay, the hydrogen chloride version of the amino donor, okay, and then ammonium salt, okay, and then urea derivatives coming from the fragmentation of TBTU. All these will be dissolved in DMF. We specifically choose this solvent for the reaction because it's such a powerful solvent, it's so polar, in other words. Unfortunately, it is also carcinogenic, and that's why I want you guys to pay attention to the solubility. I actually lecture about that, okay? I said there is a big reason why we want to choose DMF. Look at the solubility, and I want you to find, during the lecture I said, please look it up, okay? And I give you a hint right there. It is all because it is a good solvent for you to get rid of all the garbage, okay? And then you can keep the product in the ethyl acetate solvent. Okay, you use ethyl acetate to extract your solvent, extract the product too, the dipeptide product, okay? And this, because it is a carcinogenic, and of course you have to get rid of that. And so you rely on water, couple times washing. Okay, so if you look at the procedure right here, after the reaction, okay, ethyl acetate to extract your product, okay, wash the mixture twice with, okay, now this is the acid you use to kill ammonium. Well, actually it is the, right here, triethylamine turned into ammonium by protonation of HCl. Okay, so you add water later, okay, to get rid of all the acid, and then the DMF at the same time. So all the garbage, okay, all the undesirable fragments of ions, okay, and this amine and then DMF will all drain in water. And as a result of that, this ethyl acetate has actually very, very simple composition right there, okay? It has your desirable product, okay? Of some, maybe some unreacted product one right there. And so you rely on your purification process to take care of that, okay? So people make a mistake here for not looking up. Why did we choose this, okay? And when this is mixed with water and then HCl, okay, they actually are miscible. When you provide acid or base, they must come in the water phase, okay? HCl or this potassium bicarbonate, they always provide acid or base, this kind of a, you know, inorganic acid or base, they always come in aqueous condition. And then, okay, you can get rid of the DMF in the aqueous condition, okay? Now you use water. After so many times in the aqueous washing, extraction, and then acid-base reaction, okay, you're able to eliminate that carcinogenic solvent. Understand? Okay? and then so you dry, etc. So what is the purpose of potassium bicarbonate here? How many people did answer that question? I can tell you a couple students did address that, okay? But I didn't really penalize students for not pointing out the purpose right here, because I think it is common sense. People should know it, okay? HCl, once you add HCl to especially a strong acid being used to take care of the purification, take care of the workup, you need to rely on a weak base, okay? Inorganic weak base, baking soda type, to make the solution go back to neutral condition, okay? Always treat strong acid with weak base later, then you wash with water, then your organic layer will be neutral. Are you all with me? Okay, and I'm pretty sure you have the knowledge. It is just because when you write down procedure and the flow chart, you don't really connect. Now I'm helping you to connect, okay? Now this is drying agent. For every extraction, you have to add drying agent to the organic layer. Then you remove the solvent in the rotary valve, okay? This is all very much standard, okay? Now here comes another one. Students totally forgot to tell me why this crude dipeptide should recrystallize. And from this recrystallization process, you're able to get rid of the undesirable racemic mixture. Am I right? You can single out one desirable product at the end and delete the other undesirable stereoisomer. So I can tell you very, very few people, okay, remember we have a, ultimate purpose right here. You actually need to isolate your desirable optical active compound, okay? You don't want the racemic mixture. You want the one that has optical rotation, okay? All right, so everything else is actually, just pretty much standard procedure. And so let me go over some other mistake here, okay? So some people didn't show me, okay, or else, oh, by the way, yeah, the HCl will have to be removed completely or else it may hydrolyze your product. Remember there is an ester group, okay? So I just wanna remind you, okay? All these small steps right here, very, very important, okay? All right, also, okay, hydrolysis. People didn't really write the side reaction. And actually the ester group, okay, if you don't take care of the moisture during storage, if you don't take care of the moisture, anhydrous condition, when you run the reaction, you actually destroy the ester right there. And then the amino acid starts self-attack, okay? So this is another important side reaction you want to mention. Okay, so one more time, let me show you right here. What ester am I talking about? Look at this. Is this ester group to you? Yeah, it is ester, okay? And then look at this part. This is amino group plus the HCl. Okay, and this HCl will be actually taken care of by the triethylamine. Your amino, sorry, right here. The triethylamine right here. Right here. Triethylamine, okay, will help to remove this HCl right here. And you want to make sure this HCl also get neutralized later by the potassium bicarbonate. Am I right? That baking soda type of base. So you can protect your ester from the acidic attack or the hydrolysis reaction. And you may say, machine, how come this molecule does not self-attack and hydrolyze itself? It is because the amino group is so polar, okay, it's capable of keeping the HCl around in the dry condition. Okay, so chemists all know this part to play this trick. Okay, block the amino group by using this HCl when they supply, the amino donor. Okay, all right. So how many? My goodness, how many students are here? Hey, I don't know what's going on today. We only have 4 students. Let me see. Let me check one more time. Okay. Are you all with me?
Yes.
Oh my goodness. 4 students in total. Okay, I don't want to wait anymore, okay? It's 11:30, and I believe I posted the meeting ID already on Beachboard, so I think they're still working on the auto report maybe. But I don't want to wait anymore, okay? Let me move forward. So I hope I did clarify peptide reaction, the second part. I hope there's no more question, okay? And I do want you to go back, okay? Check, these important things, because next week you will have to do peptide report. Am I right? Hello?
Yes, I'm pretty sure that's when it's due.
That is coming up, okay? I don't know whether this is gonna be a type report or it's gonna be I have no idea. I don't know what Dr. Lopez wants. I have no idea. In the past, we did ask students to write report, okay? And so with this Zoom arrangement, I don't know, okay? I don't know whether this online, in-class questions, it's doable at all, okay? All right, so can I move on? And can I just get on the Grignard reaction now? Are you ready?
Yes.
You're ready, okay.
But Dr. Lee-Lin, sorry, may I say one thing?
Yeah.
On my end, for some reason the internet connection is not that good today. So about 5-10 minutes ago, it kicked me out and I had to go back in.
Oh.
So if you see the number dropping every now and then, it might be me.
No.
But I'm not sure what the problem is. It might be because I have other family members that are also using Zoom.
Yeah.
So that might be why. But so if you occasionally see me leave, I'm sorry. It's probably because it kicked me out again.
Yeah, actually, I have the same problem. When I lecture on the Zoom, I have to kick everybody out. Let them take a walk, or yeah. It happens. So I don't know did you miss the part of the lecture? I don't know.
It's okay. I could go back to it because it will be recorded as usual.
Yes.
Yes, then I could go back to it. It's fine.
Okay. All right. Okay, I just gave you guys a summary on the common mistakes, okay?
Would that summary sheet also be on Beachboard?
Okay, Carissa, this is a very good question. Do you think I should post this part at all? The only thing that's holding me back, okay? I don't know whether this 420 class will be offered in the fall with the same experiments. I have no idea, okay? However, a lot of information I gave here is actually pertinent to the pre-lab writing. And if I advertise, okay, or if I make this information readily available to everybody, then I can tell you some of the students actually sell my answer key as a product to other students for profit. Okay?
Oh, I see.
And then a lot of students actually don't want to make effort and they just purchase whatever readily available to them, and they don't want to think, and they just want to get free good grades. And this has happened for quite a few years, tell you the truth, okay, especially for 420. So if I don't advertise something, especially the key, this is the only reason, okay? Okay, so
Yeah.
So I think I better minimize it now. Okay, so because I'm thinking to yeah, this common mistake is probably okay because I'm not really telling you the answer and make you write the answer according to, you know, the hint. Okay, it's not the same as answer. So I think I'm able to advertise. I shouldn't say advertise, or just release that on YouTube in the social platform. Okay, so
Yep.
we just don't want students to use this information and turn around, sell it, and then make everybody just sit at home on and not wanting to prepare themselves. Understand? This is what we don't want. Okay, so for today's video, I will upload it on YouTube. Okay, I don't mind showing this, but other things I really, if I say I cannot tell you directly, there is a reason. Okay.
Yeah.
All right. All right. Let me move on and let me talk about our next experiment. This is the Grignard, and let me go on. And by the way, is there an exam coming up this week?
Dr. Lopez mentioned that the second midterm is on, let me get my calendar.
Uh-huh. Is it sometime 27? That is 2 weeks from now.
Yes, the 27th.
Okay, so, well, I think some students just want to view the YouTube, or they don't care to take this class for credit or something. A lot of students are just doing credit, non-credit, and I had one student already drop out, not because I asked her to drop. This person just struggled too much and decided to withdraw. And I can tell you, we try to help, and this is a very difficult class. And I can tell you the coming chapter here is all on the stereochemistry. So make sure you utilize all the information I provided online. Okay. Last year, I was able to help some students get very good score in the final because they took my advice and they checked the video again and again, and then exercise, take notes, and practice. And I can tell you, just, you know, there's no shortcut for stereochemistry. For this chapter, you just have to get your hands dirty and practice. Okay. All right. So let me show you. This is what we're going to run. This is a reaction, Grignard reaction. Okay. I think you have done this before, right? Grignard, meaning that you use magnesium and then a halide. Halide means, okay, you have this alkyl group and then a halogen, okay? Halide compound as a solvent. Okay, so magnesium and then the halide actually can form a solution. Okay, forming a solution, and then it become a good nucleophile. And just look at this Grignard region right here. Okay, you see this magnesium actually sit between carbon and iodide and halogen. Okay. And how does it turn into a nucleophile? And this nucleophile will be attacking this carbonyl group, carbon right here, during the reaction. It is all because there is a change in the polarity on this carbon. Okay, I will show you the slide and I'll show you on this carbon. Actually, it become partially negative, okay? Okay, so this is the secret weapon right there, because you introduce a metal, magnesium, okay? You're able to do that magic change, okay? Carbon is usually considered, you know, not very electron withdrawing. And so how does it become partially negative? Okay, it is because of magnesium, okay? All right, so the overall reaction equation writing is showing you that you will introduce a new chiral center after this nucleophilic attack from the methyl group, okay? So originally there is one chiral center, okay, in the molecule, in the reactant. And by doing this Grignard reaction, introducing another methyl group, you create a second chiral center. And therefore, okay, there are two chiral centers now in the end product. And depending on the stereochemistry of the first chiral center, the first carbon, there is a special way that the methyl group will attack the carbonyl group. And this is the experiment that we want to show you. Yes, there are two directions possible. Okay, because I have a sp2 hybridization on the central carbon of the carbonyl group carbon. Okay, there are two directions that methyl group can attack this sp2 carbon. This is sp2. So tell me, what is the geometry of this sp2 carbon right here? What is the geometry? I'm talking about the shape. Is this
planar?
It's trigonoplanar. Okay, very good common sense. And so for this reason, the methyl group can either coming from the top of the screen. Okay, if I say this molecule right here, sp2, this trigonoplanar is actually the same as your screen. Okay, so the two directions are one from the top of the screen. That means coming from your side where you're sitting at. And the other direction possible will be behind the screen of your computer. Am I right? Of your computer screen. Am I right? Okay, so two directions possible. And we just want to show you, yeah, there are two directions for this nucleophilic attack. However, there is one desirable product. And actually, there will be one product formed in major quantity. And from this experiment, you'll find out between these two, there are only one product. Okay, I wouldn't say 100% one product, okay, maybe 95 compared to 5 or 80 to 20. There is a favorable direction of attack coming from the from the Grignard reagent, okay? So this is the whole purpose for you to find out, okay, which direction of attack we're talking about. And you will learn from this Felkin Ahn model to help you make prediction, okay? So it is not just the Felkin Ahn model, there is a Chem model, but I want to focus on Felkin Ahn first, okay? Once you understand this model, it's easy for you to learn the Chem model, which associate with chelating, okay, chelating. Okay, so one step at a time. I want, okay, right here, Chem chelation model. Okay, one step at a time, okay? All right, so what reaction do you call this? You call this Grignard reaction. Why is that? Because I'm using magnesium and the halide, okay? And in the workup, okay, when you say number 2 right here, it usually means this is my workup condition. I want to use a strong acid to work up to create the product, okay? And if you look at the Grignard reaction of this kind from carbonyl group carbon, okay, with ketone functional group, it generates an alcohol. Okay, if it's aldehyde, it also generates alcohol. Okay, and so you learned that in 320L. I'm not gonna repeat it, and I just want to show you one step at a time what Grignard reaction is. Okay, and remember, you remember this, right? Oh, wait a minute, where is it? You remember this, right? So I told you you're going to be using magnesium metal and you're using halide. And you're dissolving this magnesium metal. You dissolve it in halide. So look at this electron distribution now. You know, magnesium metal has 2 valence electrons, right? Located in the 3s2 orbitals. Okay, so there are 2 electrons. And look at the distribution later. Okay, when you form the Grignard reagent right here, you realize magnesium will lose 1 electron to, in this case, the iodine will turn into iodide. Okay, and then magnesium become plus charge because the other valence electron will form covalent bond in between. Okay, this is what people believe in general. Okay, 2 valence electron, one of them is lost to the halide, the other one is used to form the covalent bond. So a common way to write Grignard reagent is to have this alkyl group attached to magnesium with a line between, and then plus charge with, okay, with a electron distribution like this, okay, and halide. Okay, so it's like a counter anion to this big species right here. This is Grignard reagent, am I right? Okay. And I want to demonstrate to you. So when we write a chemical reaction involving Grignard, okay, take a look. The formation of Grignard reagent, okay? Look at this magnesium. Do you see charge right here? This is charge of 0, am I right? Charge of 0, because this is atom, it's not ion. Atom does not carry charge. So this is 0 charge. So we have 2 valence electron right here from the 3s2 orbital. Okay, if this is a methyl bromide, is this a good halide for Grignard reagent? The answer is yes. Okay, dissolve this metal, easy, dissolved in. But when it dissolves, it is not just dissolving, it actually rearrange the molecule like this. Okay, there are a lot of people studying, you know, the change in the orbital, etc. Okay, this is not the scope of our chapter. Okay, I want to show you this distribution of the electron pairs. Okay, you know this halide electron withdrawing. Okay, and look at the Grignard reagent right here. Look at the distribution of the electron pair right here. So tell me, what does it mean to the carbon in terms of the distribution of the electrons right here? Is it more close to the carbon side? Can you tell me yes or no? Between carbon and magnesium, which one is more electronegative? The answer is always the non-metal. Okay, I can tell you metal and the non-metal put together, it is always the non-metal being more electronegative. And so this electron pair is more toward the carbon side. Are you all with me? Hello? Are you there? Oh my goodness. Are you losing connection again? Do me a favor then, hello? Can you at least type If you can't speak, can you type and text me? Are you able to hear what I said? So the electron distribution here. Thank you. Thank you, William and Parissa. You're so responsive. You can help me carry this message. Confirm this message here. Okay, so what does it mean? This methyl group right here is turning into a nucleophile, am I right? With this uneven distribution of the carbon and the magnesium. Uneven distribution of the electron pair between them makes this carbon a nucleophile, okay? Okay, so look at this. Okay, so when this is placed next to carbonyl group and between this carbon and oxygen, you know, this is more partially positive because carbon is not as electron withdrawing compared to oxygen. And so attack, okay? So this is partially negative now. Attack, okay? I have electron density quite high right here. Attack this electron poor carbon. And I can generate this species right here, okay? Do you see this fragments right here? Okay, it's magnesium bromide, but there's only one bromine, okay? There's only, yeah, because the other electrons being used in this nucleophile, okay? All right, so what do you call this species right here? Once you make this attack, the carbon on the carbonyl group, this double bond right here will move, and then the oxygen will receive the electron pair, am I right? So you are generating, we call the species right here, a alkoxide. Have you learned that term in your life? It is called alkoxide, alkoxide, okay? So what do you want to say about alkoxide? What do you want to say about alkoxide? I will introduce my friend alkoxide as one of the strongest base on Earth. Have you heard of that in your life? The answer is yes. This is a very, 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 very strong base. You may say, Ms. Jean, I thought KOH is strong enough. Yeah, you're talking about inorganic base. Yes, it is strong. But if you want to compare the basicity, my goodness, this alkoxide is even higher. Okay? If you put this alkoxide in the presence of any hydrogen donor, alcohol, for example, moisture, water, yes, it will receive proton easily from any hydrogen or proton donor, okay? Strongest base. One of the strongest. If it's not number one, I was saying, how about top three, okay? Very strong. So obviously, when you make the Grignard reagent in the lab, you have to control the reaction condition at all time. It has to be anhydrous. It has to be moisture-free. If you have moisture contamination right here, guess what? The Grignard reagent will die right there, okay? You will not make alcohol from the desirable product, okay? From the, you cannot make the desirable product anymore, okay? The presence of strong base will just lead the reaction sideways, okay? If you don't take care of this moisture control, okay? All right. And so the end result is you want to create alcohol, okay? But you want to protonate it the way you want it, okay? You don't want moisture there, okay? You don't want H2O here because you don't want that H2O to lose that hydrogen and then create a strong base, OH minus there. Then the reaction will go very weird. We have alpha hydrogen here, right? That OH will attack this guy and then do something weird, okay? A lot of the side reaction can occur. All right, so in writing this pre-lab, okay, you know this is a moisture sensitive species, okay, you know that. So go ahead and write that side reaction, write any undesirable product, okay? And look at also here, when you introduce, okay, the Grignard reagent like this into a carbonyl containing compound, okay, drop by drop, you control the reaction rate slowly. Okay, you only want to produce this alkoxide slowly, because I can tell you this is a actually heat releasing reaction also, and you don't want to form you know, a side product, side reaction, and you don't want to you don't want to lose your ether. You'll be using ether, and this is a very low boiling solvent. Okay, so any heat control, okay, it's important in the Grignard reaction as well. Once you lose the ether, then you'll see, my goodness, magnesium and all these halide, they don't dissolve anymore, okay? They don't have solvent there. There's no reaction. The reaction will stop, okay? So heat control is quite important. On top of that, okay, it's a safety issue. On top of that, okay, it is a matter of, do you want to create only the side product, not creating the desirable, okay? All right, so we just, you know, this is the key step, okay, of I would say there's two. The top two steps are critical in terms of creating a successful Grignard product at the end, okay? All right, so this is only one chiral center I'm showing right here, but in our experiments, we actually have two chiral center, and I'll come to that later, okay? And so here, once you finish adding your benzaldehyde or, you know, any aldehyde, or in our reaction, in our experiment, we're introducing ketone. Okay, you're adding this drop by drop, okay, into the Grignard reagent. Okay, if you finish that, you allow the reaction mixture to stir a couple, like 20, 30 minutes. Then you can pour this mixture out, and then you prepare your acid, and then you protonate the alkoxide, okay, at the end. You create your alcohol this way, and you want to do this in the ice, very low temperature condition. Again, this is a strong acid, okay? And when it meets with the reaction mixture like this, it generates a lot of heat, okay? So you need to keep the temperature very, very low, very, very low, okay? And so this is the general, I would say, the general guidelines how to run the Grignard reagent. And let me go back to the lab manual one more time, okay? Okay, did I show you? Oh, yeah. One thing, before I show you the lab manual, and I think you have your lab manual with you too, okay? So I want to show you one more thing. Okay, look at the Grignard reagent is super sensitive to hydrogen donor. I told you that already. And I just want to show you example right here. Okay, so for example, this is a methyl group. Okay, and so magnesium dissolved in methyl bromide, and you get that reagent we call Grignard reagent formed. But if you encounter a contamination situation where there is acidic proton around, and because of this hydroxy group right here, what's gonna happen here is this is again partially negative, right? Partially negative on the methyl group, and it steals the hydrogen proton. So what's the byproduct here? It will give you methyl group, am I right? And hydrogen together. So it is methane gas. Methane gas form in this reaction. So the common sense is the Grignard reagent and the hydrogen donor together, okay? If it is coming from acid or any hydroxy group or alcohol, it will give you, yes, alkane. And alkane, small molar mass alkane is usually bubbling gas. Okay, so you will smell it. Okay, you will smell methane in this case when you have this contaminant, acid contaminants. Okay, all right. So this is usually indication, yeah, contamination. All right. And why do I have to point out this? It is because when I show you the lab manual, you will see. Okay. All right. Do you see something funny here? In the reactant, okay, I know this carbonyl group will be receiving the nucleophile. Is there anything else in this molecule that will be sensitive to the Grignard reaction? Hello? In this reaction,
The OH group?
yes, that OH group. This OH group will be, yes, contributing some hydrogen plus, and then you will see what kind of gas. This is called methane.
Methane.
Yes. So CH3 will meet with this hydrogen and produce methane gas. Okay. And go ahead. I want you to write down. Okay. Methane gas is going to be a bubbling product. Okay. Why do I want to show you this? Okay. It is because right here, I think we have a typo right here. Let me close this, okay? Do you see, there is, okay. I think there is a typo in the past, but let me see if it is being corrected in this part 2, benzoin right here. You see ethane evolution right here? It is telling you ethane, this is alkane, am I right? So this is a mistake. It should be methane, right? Okay. So some people ask me, Ms. Jean, where's the ethane from? I have to make that correction, okay? I can tell you it is not ethane, it is methane. It is coming from this methyl group and then OH, okay? So I told you this hydroxy group is sensitive. It's sensitive to Grignard reagent, okay? So this methane gas is actually bubbling. All right, now ladies and gentlemen, the good news is we're using ether. Okay, now try to understand. You're using a very, very volatile solvent. What is it? Is it ether? Anhydrous diethyl ether, right? Boiling point of 37 degrees C. Body temperature, or maybe 36 or 35. I don't quite remember. It is actually boiling point, the same temperature as your body temperature. So when you hold diethyl ether in your hand, it boils off. Okay, if you hold it long enough, yeah, the whole flask of solvent will just evaporate. Okay, crazy, right? And this is actually very flammable. So there is a big fireball potential right there. And on top of that, you are creating CH4, the methane gas. Is that double congratulations? So I can tell you this reaction is super flammable, understand? I have to alert you that, okay? I'm your lab instructor. I can tell you chemistry is for you to always stay alarmed. You will learn to stay alarmed always. Look at the potential explosion here and there, okay? All right, so I have already emphasized the safety issue, and I want to move forward, okay, and talk about what you need to learn, okay? Hold on, let me check what's in here. Okay.
A question about what you just went over.
All right, sure.
For the
let me give you the, yeah, here, okay.
So when we do the workup, should we show that the OH is attacked and then have it like that until
yes,
till the end of the reaction?
That is attacked, definitely attacked, yes. It's not going to be shy, okay? You think this reagent will just, you know, be conservative and stand behind the scene? No, very, very aggressive actually, okay? Okay.
Thank you.
I will show you later, and I think I will reserve this part until maybe Thursday. Yeah, this is the day you have to turn in your pre-lab, right? Thursday. And the Thursday morning, I will give you some more education about the mechanism, okay? I don't want to give you too much education on one day. You will die, okay? You won't like it, okay? All right, so next is for you to learn about this model. Okay, today I want to emphasize this because if you know this, you know the other two very quickly, okay? All right, are you ready to go? Hello? Any more question before we step into this very dry model? It's not dry, it's fun actually. Let me get some water, okay? I will let you think about it. All right, can I move forward and talk about the Felkin Ahn model? All right, now, ladies and gentlemen, I want all of you to check the video I have already uploaded on Beachboard, okay? That's a very, very important video. And I think I gave you two. I may give you another one, okay? It is because one time, or for two times, I help Dr. Nagayama or Dr. Lopez proctor the final exam. And when I look at the final exam questions, I saw this whole bunch, a whole bunch of questions coming from these models, okay? Okay, so I know this is what they like. They want to emphasize, you know, you actually learn to predict the stereochemistry of a chemical reaction. Okay, so what is the purpose of these three models right here? And in fact, there will be another model, okay? It is for you to make prediction. What is the more favorable product? When you know there will be two directions of the nucleophile coming from the Grignard reagent, you can attack from the top or the bottom of this sp2 plane. Okay, you know there are two directions, but there is a way to predict which one is more favorable. Okay, and in fact, in the lab, we're able to show our result is very, very consistent with our theoretical prediction. Okay, all right. So let me show you the Felkin Ahn model. Okay, are you ready to go? I want all of you to have a piece of paper next to you. I want you to open the lab packet, page 38. And I want your pencil and color pen ready, okay? All right. So what does Felkin Ahn model show you? We will tell you whether this is a syn attack or anti-attack. You will learn that later, okay? Don't worry about this term yet, okay? The main thing is you already have a first chiral center in the molecule of the reactant already. So when you introduce a nucleophile to attack the carbonyl group, you're creating another one, okay? Just like what we show here, okay? And go ahead, and this is what the nucleophile will see, okay, when we run the reaction, okay? One more time. This is similar to what we have in the lab. Am I right? Are you looking at the lab manual now? We have a carbonyl group next to a chiral center. Am I right? Do you agree with me? Okay.
Yes.
Yes. Okay. And so go ahead and draw that three-dimensional picture of this chiral center. And you want to also draw the three-dimensional picture of this carbon as well. This is what you're going to see. Okay? And don't worry about the distribution of the substituents yet. I want you to know, for you to learn about this model, okay, now you have this carbonyl group. The way to draw a carbonyl group, you always want to point upwards, point to the sky. And I told everybody, you have to say hallelujah at the same time, okay? The carbonyl group is the one that determine the, you know, how you want to draw the risk part of the molecule. This is going up, okay? It is just like when you draw the stereoisomers, when you do the, I wouldn't say Newman projection, how about Fisher projection, okay? You always want to draw a carbonyl group pointing upwards when you draw sugar or amino acid, okay, in biochemistry. Carbonyl group always point to the sky, okay? All right, and this carbon at the same time has hydrogen, am I right? And so if you view this, this carbon from the side view angle this way, you will see 180-degree distribution. That's from your view angle. Am I right? Okay. At the same time, this carbon right here, which is the chiral center. Okay, now look at the distribution of phenyl group, hydrogen and methyl group. Okay, you go ahead and determine this is actually coming from, yeah, is this clockwise or counterclockwise from the smallest to the biggest? Okay, if you stand here where my hand is pointing, right here, if you view the molecule from this direction, okay, the carbonyl goes up hydrogen goes down. This is from the view angle, okay? And then look at this phenyl group, hydrogen and the methyl. You'll realize they go by this sequence, okay? Are you all with me? Okay, so I'll call this hydrogen is the smallest, am I right? The smallest to this, the medium one is methyl. And then to the phenyl, okay, the smallest, medium, and the phenyl, it goes clockwise. Am I right? From this angle, from where my hand pointing at. Are y'all with me? Do you agree with this arrangement?
Yes.
Okay. So Felkin Ahn is asking you to do this, okay? Okay, now go ahead. If you have the handout already printed out, I have already uploaded this whole thing on the beach board, okay? If you print it out, go ahead and you'll find this is the right way to draw it, okay? So when we do the Felkin Ahn model, carbonyl group goes up and the other group, okay, is 180 because this is from the view angle, you will see that, okay? I think someone from my class last year asked me, Miss Jean, is this true? Why is it 180? And I just showed the student a pair of scissors. Okay, you know, when the scissor blade opened, okay, you will see this, the blade goes, oh, you can see, it's showing me a cross. It's showing me a cross when I open the scissor, am I right? But if you view the blades from the angle of the tip, you will see that 180 degree of the blades. This is like, okay, this is like the blade of the scissors. When you're looking from the tip, this is the 180 view angle. Are you all with me? Do you know what I'm talking about? Can you type and reply back? Yes, you get it. Thank you. Okay, Carissa, are you able to concur?
Yes. Sorry, my computer is slow as well, so.
Okay, so we're doing this model, okay? This is number one, you do. Number two, you do this. It's 180. Then what's next? Step number three is for you to put the largest group of the chiral center 90 degrees to the carbonyl group. This way or this way. Are you with me? Okay, so step one, hallelujah. Step two, view angle from the tip of the scissor, okay? Number three, put the largest group of the chiral center right here. This is the largest group of the chiral center. You do that 90-degree angle either on the right hand or it will be on the left hand, okay? We are trying to give you the structure, what the nucleophile will be experiencing later, okay? It is the structure when the nucleophile come close to the reactant molecule, it will see this picture. Are you with me? So do you see this small, medium, large, clockwise, small, medium, large, clockwise? The only difference is I will put my phenyl group, the largest group on the chiral center, 90 degrees. So I have two choices. Okay? This is all coming from the conformation, right? This is actually single bond rotate against each other and I can get each other. I can get the molecule this way or this way. Am I right? This is coming from the conformation. This is not the end of it, okay? Now here comes the nucleophile, right? Where's the nucleophile? Hello? This is my nucleophile, right? Okay, in this case, it is our methyl group and then some metal. Okay, how about our reactant? Sorry, I shouldn't say the reactant. The Grignard reagent on our lab manual. What is our nucleophile? Tell me. On page 38, what is the nucleophile?
The methoxy group.
The nucleophile is actually from the Grignard reagent, am I right? The Grignard reagent, that is actually number 1 on top of the arrow. Am I right? Hello?
Yes.
Yes.
Okay. Or you may say, Miss Jean, can I just say it is methyl group and I say methyl and dot dot. Can I write that way? It is not the best way, okay? But I'll give you credit, okay? You're 95% right. But this methyl group dot dot is still connected with maybe some dot line relationship with the magnesium, all right? Are you over with me? Okay. Anyway, are you all convinced? Okay, this nucleophile will see either this kind of a arrangement of all the groups on the 2 carbons, or it will be this way. Okay, you may say, Ms. Jean, okay, there may be some rotation in between, but I can tell you the critical moment is determined by this picture or this picture, okay? The critical moment where the product will be formed will be determined by this arrangement or this arrangement, okay? All right, so one more time, let me repeat. Step 1, carbonyl group, point to the sky, the other one and 180 degrees. Step number 2, heaviest group, 90 degrees from the carbonyl. Phenyl, 90 degrees to the phenyl. Okay, number 3. Step number 3 is this. And follow me. Right here. You want the new bond, or you want the nucleophilic attack to produce classic tetrahedral bond. So it will be roughly 107 degrees relative to what? Relative to the carbonyl group. Am I right? It is this carbon that has carbonyl group you want to create a tetrahedral. Am I right? And so I want 107 degrees. Now, ladies and gentlemen, okay, so I have 4 pathways to do it, okay? Do you see where my hand is? Okay, this is the carbon that will need to transform from sp2 to sp3 now. And it is welcoming a nucleophile. And the nucleophile will have to approach 107 degrees relative to what? Relative to carbonyl group. Okay? It is 107 relative to the CO2. Okay, so 107 degrees. Pathway A will go this way. Okay? This is about 107 degrees. And pathway B will be here, 107 degrees. Okay, so A, this is one pathway. B, another pathway. Here, another, I'll say pathway C. and pathway D. Why do I have to show you this? Because there are steric hindrances I will have to consider. So I want to give you, okay, this clear three-dimensional drawing and help you determine pathway A, B, C, D when this nucleophile come close to the carbonyl bond. It has to be 107 degrees. And so A, B, C, D between this four pathway tell me which pathway will be least hindered. That means most favorable. Tell me between A, B, C, and D, which one is most favorable? Can you text me back? William, thank you. I want to give William 1 point. Bonus point, 1 point. Okay, William, you got me, yeah, very, very happy today because you clearly registered the message. And pathway A is most favorable because if the nucleophile comes this way, there are only 2 hydrogens in nearby. And it does not give me much repulsion or steric hindrance. Am I right? It's not going to be crowded. It's not going to be crowded, okay? How about this way? Wow, you see this phenyl group? It's making the space actually quite crowded here. The pathway C right here, also hindered by the phenyl group. Pathway D, don't forget, I want 107 degrees because that is the tetrahedral structure, okay? And you will experience some repulsion coming from the methyl group, and therefore, pathway A, this attack will be most favorable. Am I right? Are you all with me? Hello, everybody?
Yes.
And if you don't believe me, I'll give you the drawing right away. You see that? This is most favorable, okay? And we call sing attack. And well, let's worry about this terminology later, okay? This is most favorable because there's not much hindrance here. Okay? And look at this. So nucleophile will come in and will make this hydrogen nucleophile, and then the oxygen, and this oxygen will turn into alkoxide, am I right? And then will turn into OH group at the end when you introduce the acid in the workup. You realize the methyl group is actually in between hydrogen and the OH. It is referring to this carbon right here. Methyl group coming from the nucleophile is in between hydrogen and the OH. Okay, so this sp2 now turn into sp3. Am I right? You may say, Ms. Jean, how come this is not 109 degrees? This looks to me it is 120. Don't forget, this is view angle. It's not the actual bond angle, okay? This is a view angle. Put it this way. If you view a person's face from front, you see everybody has flat nose, okay? But if you look at the person from the side, then you will see, hey, this guy has a really, really nice curved nose. It's not flat, okay? This is all bond angle, okay? It is all bond angle compared to the view angle. They are not the same, okay? Okay, I want to show you this right here. Coming from pathway D, is not as favorable because it's actually showing this repulsion. And we give you a red that some dots, red dots right here, showing, hey, there's some repulsion. Okay, so far so good. All right.
Yes.
Okay, so from here, okay, this is the pathway at A, okay, Lee's hindrance. I can write the structure for the product, okay? And I want all of you, please, okay, block the answer right here. And I want you to write from here, okay, without looking at the answer, without looking at the answer. Are you able to come up with the same structure of the end product? I want you to do that as a homework. Using what? Using the molecule on page 38. Are you with me? I want you to do that. After today's lecture, I want you to use the reactant molecule on lab manual page 38 and give me the prediction of your product, okay? It's not gonna be this molecule, okay? It will be either this 2A, molecule 2A, or 2B. And I already told you, there's one product far more favorable than the other. So the whole experiment is for you to determine, are you able to find the Felkin Ahn model? Okay, can you find this model work for you? And I can tell you, based on the students' results from last year, our end result is very consistent with the theoretical prediction. So this model is quite powerful. Okay, all right. Let me go back. So what is your homework? Okay, besides you want to start writing, hey, the pre-lab, write the reactant, write as balance equation, write the purpose. Okay, write procedure. Okay, you already know the site reaction. You know the mechanism already. Okay, etc. Okay, go ahead and predict. This is not going to be a part of the grading, but I want you to do it. If you don't do this exercise yourself, I can tell you, it doesn't matter how good I am. I can continue lecture for another 5 hours. You will not get it unless you do this model yourself and make that prediction, okay? And so how do you do it? I already give you the example. This is already uploaded on the Beachboard, okay? I want you to follow this. Okay, carbonyl, and then the other group pointing down 180 degrees. Then the heaviest, largest group, 90 degrees to the carbonyl, okay? Then you will see, hey, the nucleophile will see this three-dimensional picture this way. Then I will attack this carbonyl group 107 degrees because that is the tetrahedral angle, bond angle. I will do that and create 2 isomers potentially. Then you can determine which one is more favorable. The one that is more favorable is the one that is experiencing least steric hindrance, okay? And you know it is pathway A, doing that, okay? I remember when I lectured this last year, some student says, Ms. Jean, we know about this bond angle, okay? It's 107, it's 109, it doesn't matter, okay? It is in this range. How come we don't want the nucleophile coming from this way and this way? How come? Besides the bond angle consideration, how come we don't attack this carbon this way or this way? Are you following my hand? I'm talking about coming from this very narrow angle without considering the bond angle. Yeah, I think the student asked me the question in a very, very intellectual way. They were saying, hey, when collision occurred, the molecule would not know I have to receive you with a certain angle because we're all under this, mixing condition. So it's bombardment between two molecules. So how does it know to receive the nucleophile with a certain angle? I can tell you, this is a very good question from the student. I actually asked my professor in the past the same way, the same question. How come it doesn't attack this way? I can tell you, it is very, very straightforward, okay? It must come this way because look at this. The double bond is very electron rich and your nucleophile is very electron rich. They repel each other already, understand? They would not like to be, coming from the direction that it's already very electron rich. They actually naturally repel each other. So it has to come from the other way, from this direction where it is not the double bond. Are you all with me?
Yes.
Okay, so I can tell you in learning chemistry, you realize everything makes sense, okay? Everything makes sense. It's actually a matter of common sense, okay? So go ahead. I want to leave the question. On page 38, you have 2A and 2B. Lab manual will give you two drawings. There is only one product that will be collected in major quantity, okay? And I want you to tell me which one that is on Thursday, okay? This part will not be graded, but it will only help you to learn the last portion of Chem 420 theory, okay? It is all stereochemistry, and this is I would say, a big building block for it, okay? All right, so go ahead and find, okay, on this lab manual, page 38, the starting material, go ahead and draw this, okay? And I will just, I think I will just stop right here. In terms of the theory, okay, I can show you there will be more Felkin Ahn application of Felkin Ahn, and there is chelating theory, okay? And this is Crane model, okay? I gave you all the information already, and go ahead and digest this part first, okay? On Thursday, I'll talk more on this model, okay? So far, so good? Is there any question? Is there any other question? All right. If not, let me go back to the lab manual one more time, okay? And by the way, does it help you to understand a little bit what what are we supposed to mess around with? This is a very good experiment, okay? I love it. It looks, just like another Grignard reaction, but there are a lot of theory, that you can enjoy. All right, look at this magnesium turning right here. This is actually in the procedure. Preparation of, this is the Grignard reagent, okay? Methyl magnesium iodide, okay? You should know methyl iodide is actually potential carcinogen too, okay? And how often did I say that? Whenever you have this, you have this contaminant coming from, oh my goodness, coming from a poor workup, and you want to sell your product to your customer, you better be careful, okay? You don't want to get sued, and make sure you take care of all the impurities. The magnesium turning right here, okay, I think you've seen this term already. This is actually magnesium, because it is a soft metal, okay? Magnesium is not a strong metal. It's not like titanium, okay? It's not like iron, okay, they're very rigid and ductile at the same time. Magnesium is soft, okay. So whenever you shape it, you realize the metal actually turned into a coil, or it's easily shredded like noodle. And so when we receive this magnesium metal from the vendor, okay, sometimes they're in chips because we have to chop it down because they're all in coil form now. So why don't we just chop it down? And then we have to polish before use. Magnesium, in order to be used in the Grignard reagent, you have to make sure magnesium surface is clean and it's pure metal, not magnesium oxide covered, okay? And magnesium easily oxidized to MgO, magnesium oxide. And that ionic compound, which is a salt, basically, it covers the surface of the metal. I can tell you that will actually block the Grignard reagent formation, okay? It does not have this magnesium fresh metal surface. So what we do is we usually pound or we hammer it, okay? We want to knock off magnesium oxide layer from the surface before use. Okay, so this is why we call it turning, because a student asked me, okay, Nasreen, what is turning? Okay, and to chemists, this is common sense, okay? It is just like aluminum metal, okay? It also oxidizes easily to form aluminum oxide. Al2O3 is the structure, okay? And it forms a layer on the surface of aluminum metal. And so unless you polish it, use sandpaper or you hammer it, okay, and you can pulverize the surface oxide layer, and you can use the metal only after you get rid of that oxide layer, okay? All right, so this is a big preparation step right here. It looks easy, but it's actually quite sophisticated, okay, when you work on this, okay? And I told you there are a lot of safety issues associated with this, okay? The flammability, etc. Okay, but everything else is just okay. It's quite, the workup after you've done this peptide 2, I can tell you this is nothing, okay? You should be able to handle this yourself, okay? And we talk more about the Grignard reaction later on Thursday. And for now, I don't know whether you have any more question before I dismiss the class. Okay, don't forget, I want you to make the prediction, okay? Which one is your product? This is not a 3-dimensional drawing. Okay, I want you to pay attention to this first chiral center right here. This is where I'm pointing at. This is her first chiral center, okay? And you see between these 2 stereoisomers, they have the same geometry on the first chiral center, okay? And you want to make prediction of the nucleophilic attack. How do you produce the product? And which product is more favorable? We're talking about the second chiral center. Okay? Am I clear now?
Yes.
Okay, any other question here?
I had a question. I ran out of pages in my lab notebook. Would it be okay if I did the next pre-lab in my spiral?
Oh, guess what? Yes, I will let you go. Okay, yeah, no problem. But you only making copy, right? In order to submit the pre-lab assignment, you're making the copy, right? So I can let you go. No problem. Yeah.
Yes.
Okay. But for resume purpose, you may want to put all the information in one place, okay?
Yeah, I was gonna get another one. It just hasn't come yet.
Oh, don't worry, don't worry. What I'm saying is, I call this lab notebook as a resume, okay? It is a resume, tell you the truth. I remember one of our TA, our GA, also, yeah, TA and GA, instructor for 223A and 223B. Okay, this person just told me last year before a job interview, I said, hey, you know, because our TAs usually, they tell me what happened to their career life too. And we were just chatting about this lab notebook, and this TA just told me during the conversation, guess what? During my job interview, the interviewer were asking me that I bring my lab notebook because they want to see it. So I'm not creating rumor. This is real. People want to see your work habit. They want to see your personality just by looking at your lab notebook. Okay. All right. So yeah, I strongly recommend you keep everything in place. Okay. All right. And I think for now, I just want to stop right here. And I'll continue with more stereochemistry next time. Okay, and I've noticed my class is probably ahead of Dr. Lopez's lecture. Am I right? Because he has not started we call asymmetric aldol synthesis yet. He has not, right? We call it asymmetric aldol synthesis. In other words, you're creating a new chiral center. I don't think he started yet. According to the schedule, okay, now let's look at the schedule together. Hello? Hello, are you there?
Yes.
Yes.
Okay. Let's look at Dr. Lopez's revised schedule. Okay. So this week we submit our aldol report. And then we're supposed to submit Grignard pre-lab on Thursday. And I'm halfway done with the lab lecture on the Grignard. And next week, you will do peptide report. At the same time, now this is the part, identify and prepare for oral presentation. Okay. Oh, do you see? Okay, let me open this page. You probably can see better. Hello.
Yes.
Now let's look at this. Okay, I'm halfway done. Work, write, dipeptide report. I haven't heard anything. Oh, I don't know. I don't know what he wants, okay? So do me a favor. Okay, I'm gonna go after Dr. Lopez about this part. What does it mean you want people to get started? The peptide reports. What do you want? But at the same time, you want to run after Dr. Lopez for the same thing, okay?
He mentioned yesterday that he still has not decided whether he wants us to write a full lab report or not, and he said he will let us know.
Mm. Okay, so continue your follow-up on next Monday then.
Yes.
Okay, a lot of times students write me questions on email, and I can tell you 99%, if the questions I can handle it from my own without his input, I normally respond right away, okay? It is when I have to wait for his instruction, then it's holding everybody now. And so what I'm saying is, I do respond email immediately, okay? I check my email almost every hour. Every hour I will check. And I will reply within, usually within a day you will hear from me. But if I don't reply back, it is usually Dr. Lopez is not replying back to me, okay? So I want to follow up on this dipeptide next Monday report. What does it mean? We have to submit the report, okay? Then this is the part that bothers me. Identify and prepare oral presentation. Does it mean students are supposed to submit their selected article? I can tell you the answer is yes from my own, okay? But the thing is, a lot of times he postponed and postponed. But the thing is, my advice, you better get this part ready next week, okay? You want to know what you want to present. Understand?
Yes.
Okay. And so this is the week for you, all of you, to make presentations. So we spend a week. That means 2 lab periods. So in this class, we have 10 students. So I'll say 5 students will be presenting the article, okay, on one day. The other 5 will do it on Thursday. But what do we do here? What do we do on the week number 14? I still don't know. Okay, does it mean there will be a lab period that we don't do much? I don't know. It doesn't seem to me we have a scheduled work to do on Thursday, next, I would say 2 weeks from now. I know what to do here on this week 13, but the second day of the week 14, I don't have, I don't know what to do, okay? Besides submitting the Grignard, and after you get the Grignard report submitted, I mean, that day, what do we do in the class hours? I have no idea, okay? And it seems to me I follow his schedule, and I realize his lecture oftentimes is a little bit behind, which I can understand, okay? For example, I think he's still talking about NMR yesterday, right?
Yes.
And so he will start asymmetric synthesis next time. Okay, now ladies and gentlemen, this asymmetric synthesis is a big chapter for 420 students, okay? It is all stereochemistry. And for this reason, I want to introduce a model, little by little. And instead of having 3 or 4 models all introduced at the same time, you all, oh my goodness, within the same week, if you want to learn, I think it is a bit too much, okay? So I will take my pace. I think it is reasonable for you to do Felkin Ahn at the entry level first. And then next time I'll introduce the chelating, and we can talk more next week. You need more review, okay, on the stereochemistry next time. And then it is the week after. If we want to talk about the preparation of oral presentation, I mean, each student will have their own set of, it's very hard. It's very hard for me to do individual training in the class hours, understand? So I just have a little bit of question here. So you better find out from Dr. Lopez, okay? Try to make him provide the guidelines, okay, on week 14. Of course, I will go after him for this, but you guys will have to also echo my request, okay? In order to remind him, okay? Why am I saying this? It's because I think having one instructor making noise is not as good as having the whole class running after him. I think the whole class will make it a more powerful request, okay?
Yes.
Yeah. Okay, and anything else? I think for today, I think you have enough work to do. Okay, just view the video I introduced to you and do a little bit of practice. And if you're able to make prediction of this one for the Grignard experiment, you know which product 2A or 2B should predominate in the product quantity. I think you're really good to move forward and learn about this asymmetric synthesis, okay? This is a big chapter. And I said that several times, right? This will be in your final also, and big chunk of it, okay? All right,
Yes.
all right. And I'll just say, yeah, before I say goodbye, any other question?
So you said that the Felkin Ahn model that we're going to draw in the pre-lab, that will not be
That will
graded?
not be graded.
If
but
we get it right, will we get extra credit?
yes,
Oh, okay.
yes.
Thank you.
I would like to, why do I do this, okay? This is an excellent, excellent suggestion from Carissa. Yeah, I will offer this opportunity to students. If you're able to show me why you come up with the answer, you got it right, and you can give me some explanation, I will give you bonus point. How about that? Is that okay?
Yes, that will be great. Thank you.
That would be great. Okay, all right. So I'll just leave this opportunity to students then. You know, instead of me explaining again, lecture the same thing. Yeah. It would be nice if you can participate a little bit. Okay? All right. All right, before I say goodbye, anything else?
And Dr. Lopez has not gotten back to you on how we will do the oral presentation? Because yesterday during the lecture, one of the students from your section said that your class was thinking of doing just recording
No, I
the
did.
presentation.
One of the students wanted to make that suggestion.
I actually like that idea. And when we discussed it in Dr. Lopez's lecture yesterday, he said that he will consider it, but he also likes the suggestion. But he said he will get back to us on it.
I like that suggestion, but the only problem is, let me tell you, the only problem is when you make oral presentation, I can tell you in the real world, when you give a seminar or something, people will ask questions from the floor. And it's a random direction, okay? People will challenge you, or they will, hey, you know, something you didn't say clearly, can you clarify this? And I can tell you, if it is just a recording, you don't interact with the audience. That is not real, okay? That is not at all. No, in reality, my goodness, yeah, you get challenged, okay? It is just like preparing your thesis defense. You have to defend it, in other words, okay? You learn a little bit how to defend it. We don't expect a high level of professionalism at all. No, but this is the training opportunity. So instead of giving you a unreal world, why don't we give you a real world? And you're facing only 10 students or 12, including the instructor. This is actually better training than, you know, record everything and then you just say it and, you know, as if we all understand. No, this is not at all the reality. This is not at all the reality, okay? So I'm not saying I'm against it. However, by considering how difficult it is for students to make presentation on a Zoom setting, I think it is difficult.
Yes.
Yeah, can you imagine? Yes. We all talking to a screen.
It's actually much, in my opinion, it is more intimidating to do that than to actually go up in front of an audience.
Yeah.
At least that's the case for me.
Yes. I can tell you, even for instructors, for us to make presentation on the room, on this Zoom setting, it's not easy because actually when we face person to person, I from your facial reaction, I can actually tell whether you understand it or not.
Right. Yes.
I can work on my weak point, okay? But when I face only the screen, I have no idea. I'm just talking to myself.
It might also be because me as an audience, I am used to just nodding my head if I understand something. And then and I realize, oh wait, no, you can't see me if I do that.
Yes, yes. So have you noticed a lot of times I just make sure, did you get it? Did you get it? And I stop and check and make sure, you know, I'm slow enough to, you know, make this message clear. I think I'm okay. I think so far I'm still, I think if I'm able to receive some reply message saying you understand, I think I'm happy, okay? I can tell you the dipeptide reaction to, I can tell you that is the killer chapter. It is so hard, okay? And then the stereochemistry, oh my goodness, it's so hard to just talk to screen. You know what I mean?
Yes.
It's so hard. Yeah, I would rather write something at the same time and have you guys, you know, get your hands on the paper and do the same exercise. You know, when I lecture this asymmetric synthesis in the past, I asked my student to just draw on a piece of paper, and I check individually in the class what their drawings are, and then I can correct their problem on the spot. Okay, that is better than asking you, hey, exercise at home, and then let's see next Thursday what you have got. Okay, it's not the same because I know students nowadays prefer to get some alarming signals when they make mistake, and yeah, instead of learning like walking on the desert until when they arrive to the wrong destination, they have to start over. That's hard. Yeah, I try to prevent that, and I think you know, from my pre-lab grading experience, and I found the class average around 6 for that pre-lab. I can tell you, I was so happy. I can tell you, I was
for the dipeptide.
The dipeptide reaction too. Believe me, the class average is usually below 5.
Oh,
it is so hard. Yes, okay, and I can tell from those students who are making the effort, they got the message. It is just some minor detail they forgot to write it down. But I know they got the message, so I'm so happy. So in other words, if the pre-lab of reaction to a peptide, if you're getting 7 points and up, you're A student already, because the challenge, the level of challenge of that chapter, understand? It's not easy. It is not easy at all. Yeah, it's just a lot of details. But anyway, I'm happy. I you know, I have to say, the students here really have great potential. Really, you guys have great potential. It's only matter of practice. You'll get there. Okay? Aren't you glad to hear that? Okay.
Thank you.
Yeah. Okay. Anything else? Hello. If not, I'll say goodbye and I'll leave it on maybe the answer for molecules between 2A and 2B on the lab manual. I want you to pick the answer and make presentation. A small explanation offered. Okay, I'll give you bonus point. Okay, is that okay?
So we just write it down. We just write down the explanation on our notebook for the pre-lab.
On your notebook, and then prepare to show everybody. Okay, how you come up with that answer.
We could just verbalize it, right? Or do we have to actually show
Yeah, you can write on a piece of paper and show everybody,
Oh, okay.
or you can just do this then. You can. I'll do that to everybody. I'll offer the same opportunity to Monday class too. Okay, if you think you know how to present the answer, can you give me your drawing? Okay, remember the pathway A, B, C, D? Okay,
Yes.
you do the same drawing, and then you give me your answer at the end, and you pick either 2A or 2B. And if I like your answer, okay, I'll post your drawing on Beachboard, and I'll let you make presentation, and I'll give you bonus point. Okay, I'll invite everybody to do so. Okay, is that okay? And whoever interact, just like William already got bonus point picked up today. Okay, anyone who can interact with me on the Zoom lecture, I always record it and then I reward you, because I know a lot of you actually, you deserve better grade than what the score from the in-class questions, or some reports you probably don't do well. But I want to offer this opportunity for you to make up some points. Okay? Is that great? Yeah, I think it's fair. Okay? All right. So class, I will see you on Thursday then. Okay, so send me email if you want to be the first one making presentation of the answer. Can you send me your drawing, and I'll just, yeah, I'll let you make presentation. Okay.
Just send it by Thursday then?
Yeah.
Okay.
All right. All right. Thank you, Carissa.
Thank you.
I'll see you guys on Thursday then. Bye-bye.
Thank you.
All right,
Have
thank
a nice
you.
day.
Have a good one. Bye-bye.